Welcome everyone to this EawagSeminar. It's a great pleasure for me to introduce Frederik Kratzert. Frederik is a researcher at Google in Vienna, and before that he did his PhD at the Johannes Kepler University in Linz. I guess many of us have seen the disruptive behavior of machine learning in many fields, and I think it's fair to say that Frederik was among those who disrupted hydrology. In hydrology, it was one of the long-standing open problems how to make predictions in ungauged catchments where you don't have observations of runoff to calibrate your models, but you have to use catchment properties to make your predictions. And in a series of recent papers, Frederik and his co-authors have shown that if you just throw enough data onto machine learning models, they somehow manage to learn the intricate ways in which catchment properties influence the rainfall runoff relationships in ways hydrologists couldn't. And so I think this was a big leap forward for hydrology, and at the same time it has launched the discussion whether we still need hydrologists in the future, or whether these relationships are maybe just too complicated for the human mind to grasp. Of course, throwing data at machine learning models is more complicated as it sounds. So there's many knobs you have to turn, and Frederik and his colleagues were very successful in doing so. And this has inspired a lot of new research also here at Eawag. So I'm very pleased that he's here today, at least remotely, to tell us about these LSTM models for rainfall runoff modeling. Please, Frederik.
Yeah, thanks for the introduction. Let's start. So today I want to cover two different topics. The first of which is model interpretability, and can we actually learn or extract anything useful from what the model learns internally? And the second topic is one of my current favorites, which is why you should never train an LSTM for a single basin. Okay, and that's actually the topic I will start with. And I have not included an introduction to LSTMs and hydrology and rainfall runoff modeling, as I assume most of the audience at least know about hydrology and rainfall runoff modeling. And I also feel like most of the people have heard about LSTMs at this point. If not, I'm happy to answer any questions later. And I think for what I'm going to present, it's not necessary to understand like how the LSTM works in general. Okay, so let's start with the state of hydrological modeling, and specifically regional hydrology, hydrological modeling, when at the time, like when I started my PhD, which was like in 2017, 2018, but I think what I'm showing on this slide is still true today. So what we are seeing on this slide is a CDF, a plot of the cumulative density function of two different models. Both of these models being trained, one for each of hundreds of basins individually, which is the dashed line, and ones with a model regionalization scheme, which is the solid line. And the x-axis shows the Nash Sutcliffe efficiency, and for CDF plots, for people who are not familiar with them, the further lines to the right, the better the model. So what we're seeing here is the VIC model and the MHM model being calibrated in over 400 basins. And we can see that if we, for example, draw the horizontal line at 0.5, and then the lines, the intersection that we get corresponds to the median model performance, we can see that the per basin calibrated hydrology model is generally much better than the same model being trained in a regional fashion. And I think this is not only true for these two models, but this is true for any hydrology model, any conceptual, physically inspired hydrology model. So why are hydrology models, regional hydrology models, and regional modeling important? So this links to my current job at Google, and I think there are many applications where regional modeling is important, but one specifically is flood forecasting. So floods are still one of the most common and most deadly natural disasters on the planet. And every year, millions of people are affected, thousands of, 10,000 of people die, and we have a huge economic loss every year. The thing is, much of this harm could be preventable, could be prevented if we would have early warnings in place, like flood forecasting systems that give people time to evacuate early enough. However, the problem is that in most of the places where some of the deadliest and most destructive floods occur, we actually don't have recent discharge observations to calibrate any model, or we don't have any discharge observations at all. And not only there, but in large parts of the world, the state of the gauging stations is actually declining. So this problem of not having local discharge observations available for calibrating models will become more and more severe over time, especially in regions that are heavily affected by floods. So when I started all of this, I was studying hydrology and machine learning at the same time. And in machine learning, to hear that something gets worse the more data you provide to a model is actually quite the opposite of what we are seeing in machine learning over the last, let's say, 10 years now, where specifically the subfield of deep learning has shown to be incredibly good in making use of big data sets and getting better the more data you show a model. So I asked myself, how can we as hydrologists make more efficient use of the data that we have available? Because globally seen, we have a lot of discharge data available. How can we use this data to get better model predictions? So to give like a sneak preview, first of all, the LSTM is able to become better and is doing the opposite of what hydrology models do. So here we see an LSTM once being trained in a regional fashion, and we will come to the details later, and once being hyperparameter tuned and trained individually for each basin. And we can see that the single LSTM being trained on hundreds of basins is much better than the same model being calibrated for each basin individually. And again, to the why we come in a second. If we now put this into context of hydrology models, I think many of you have seen like these results. The LSTM largely outperforms, especially regional models on the left, like which would be the direct comparison because the LSTM is also trained regional, but also on the right-hand side, this is a comparison to per basin calibrated hydrology models, which is like, again, the state of the art. The best you can do for a hydrology model is to calibrate the model for each basin individually. And even there, the single LSTM being trained on the same data on the same basins is better if you train it on all of the basins together. So at this point, many people were still very skeptical. So we're now like 2019. And like probably the most common comment I got on my work, and that every time popped up that I presented at a conference or whatever, was you're only fitting numbers. You're just chasing NSE. Your model does not understand anything and will not be able to generalize outside of the training data. So I said, what better test can we do than predicting in basins that were not part of the training data? This was initially already mentioned. And I actually now prefer this study more than we did a study back in 2019, and this is from a more recent paper from Juliana May. So this plot shows various models from the recent Great Lakes model intercomparison study, all of these models, again, the dashed lines are hydrology models that were trained individually for hundreds of basins in a data set. And then they had like a donor basin approach to do ungauged predictions. The regional models are the solid lines, and for the hydrology models, they were trained like with various regionalization schemes. I was not involved in that. And the yellow line is an LSTM. The thing I like about this figure more than what we did previously is that in this figure, all models were trained on the same data, and all models were predicting in this figure in ungauged basins. So this is like a fair comparison of how good the model is in predicting in unseen basins. And we can see quite the opposite of what was claimed, that LSTMs are actually generalizing, and they do a better job than hydrology models in predicting in rivers that they have never seen before. So I think that's quite interesting. And this will also link to the second part of the presentation, which is about what does the model learn? Like, does it learn something useful? Because clearly it must understand the system, the underlying processes. Otherwise, it would not be able to predict in a river it has never seen during training. So what's the key ingredient? Like, what is one of the key ingredients that make these regional LSTMs work? And I like to show this video. I unfortunately don't know the source. I just found it on some video dump homepage in the internet at some point. Okay, I'll start the video and explain why it's running. So what we are seeing is a lab experiment. I turn off the music. What we are seeing is a lab experiment of two catchments. They are like characterized by the two boxes. And both of these catchments get the same meteorological forcings, like they're in the same room, same temperature, and they get the same precipitation. And we can see how both of these catchments react completely differently to the same meteorological time series. So the left box is immediately draining all of the water from the upper tube, very muddy water, while the second box on the right side is just now starting to slowly drip very crystal clear water from the lower tube. So if we think about what information do we need to provide the model additional to the meteorological time series data, so that this model is able to predict the behavior of both of these boxes, I think all of you will agree that it needs to be some information about the static catchment attributes, like what, like here in this case about the vegetation, probably about the soil properties. And okay, so this is one of the key slides of this presentation. This is one slide that I would like all of you to remember. So if you want to set up a regional hydrology model, and I will hopefully convince you in a few minutes that this is the right thing that you should do, what you need is a couple of hundreds of basins. It actually works for just, it doesn't need to be thousands, it doesn't need to be multiple hundreds, but like the more the better. It's certainly true. You need meteorological time series data, but very importantly, you also need static catchment attributes. You need to let the model know, given the meteorological time series, you are in this kind of catchment. So there's a forest or there's just bare soil. And given this additional information, you should know how to predict what is happening in this catchment. If you do the same thing, but without static catchment attributes, it will not work. It will terribly fail. It will not terribly fail, but it will fail. What you're seeing in all of these slides before is always a model, a single LSTM being trained on discharge data of hundreds of catchments with meteorological data and static catchment attributes. Okay, so let's go back and let's look again why I want you all to remember that you should always train regional models. And this is also true if you are only interested in a single basin. even if you just want to model a single basin, you still should train a regional LSTM and then apply this LSTM that has seen discharge from many basins to your basin of interest. So I will make my point with a very extreme case. So what I did was I split the training data not by consecutive years into training and test data, but instead by their max annual discharge. So every year, the maximum annual discharge was below the HQ5, which is here represented by the dashed gray line, is a training year. So the orange years are training data. And all years where the max annual discharge is above HQ5 is a test year. Okay, and I made some buffer around these years so that there's no data leakage whatsoever. And then I trained two different model setups. The first model setup are LSTMs that are trained individually for each basin, hyperparameter tuned, and try to be as best as possible for each basin. The second is a regional LSTM that we collected all of these orange data from all of the basins and then again trained a single LSTM with additional static catchment attributes. So what happens to the single basin LSTM model? What you will see, and this is true always, what you will see is that during the test period, your LSTM, single basin calibrated LSTM, will not be able to predict any value that is larger than the highest value it was able to predict during the training period, right? That's no secret. That's like another critique I often heard. Machine learning models can't extrapolate. Right, that's right. So this model cannot predict values that are higher than what it has seen during the training period, but because the test peaks in this extreme case, that all of the peaks were above the peaks of the training period, we can see the saturation behavior, right? We can see here the horizontal dashed line is the maximum simulated discharge of the training period. And we can see that barely any validation point is surpassing this. So how does the same basin look for the regional model? Well, it looks like this. And the reason is because it's not extrapolating. It's not extrapolating because it has seen higher events in different basins. It has seen discharge because what's an HQ5 in one basin might be a completely normal flow in a different basin. And if you train a model on all of these gauges and data together, it will not have the saturation effects. There are a couple of other reasons playing into this, but the main reason is you have a much more diverse data set and your model will not hit this point of saturation. There's a small caveat, the saturation will still happen, but only in the basin with the absolute highest discharge, right? For everything else, you don't have this problem. And so these results, actually, that regional modeling is better than single basin modeling. These are all results that are fairly old. The two main papers were published in 2019, and then we had some discussion paper in 2020 or something. And the literature of LSTMs and hydrology is growing every year. Yet still in 2029, 80% of all hydrology papers that uses LSTMs still train LSTMs on a single basin. And I blame this to a large part on our education and on the history of hydrology, because we were all educated in the best you can do is train an LSTM on a single basin. All of our institutes have there are a couple of catchments where you have very high quality data. And usually if you do a model intercomparison study, you set up your model in your institute on the basin that you're very familiar with. Now you get a PhD student and you want him to test LSTMs, you tell him, here's the data that we use for our model, use the same data and train your model. That's wrong, and you shouldn't do it. It's wrong in the sense that you're treating the LSTM unfair. And if we would make the case the other way around and imagining that we always had LSTMs, and we now start doing conceptual hydrology modeling. And we would force the hydrology model to only model in a regional fashion and never be able to be calibrated on a single basin. Then we would treat this model unfair, right? But the same is true for the LSTM. You should treat each model in its best possible way. And for the LSTM, this is regional training. And I'm not only speaking here about better in the sense of NSE. The NSE difference is also not only explained by the peak flows, because even if we look at metrics of low flows or mid flows or bias or whatever, the regional LSTM is better in all metrics than an LSTM being trained on single basins. Okay. With that, I concluded my first part, and we'll come to the model interpretability, which I actually like a lot. I've done this quite a lot at the beginning of my research career, and I haven't done so much in this direction in the last couple of years. And actually, yeah, I would like to come back, and I hope I can like motivate other researchers to join me on this. So all of this started when I was reading about machine learning and studying machine learning, and I read this blog post that I can highly recommend anybody interested in like LSTMs in general. This blog post is explaining why LSTMs work and why they are so good on an example that is predicting the next character in a sequence of characters. So you provide the model a string of text characters, and you're trying to predict just the next character. And like this, you can generate text, right? I mean, some of these newer models are very like famous on Twitter now. So they are not LSTMs anymore, but you have probably seen these kinds of experiments. But what they also did in this blog post and in their paper was to look at how cells in the model are activated differently during the sequence of the characters. And what they found was that certain cells, so this is just one cell here that's being highlighted by different colors depending on which value it has. And they found this one cell that completely changed its behavior every time a URL was presented to the model. So it was clearly starting to track, okay, www dot, okay, now I need to like remember that the next thing will be in URL, and at the end I need to do a .com or something, right? So there was one LSTM that from all it does, like from the text, it was like just looking at some specific small thing in text data that we have. So I became interested and thought like, okay, so what is the LSTM learning if I train it on hydrology data? So what I skipped in my introduction is why I actually use LSTMs and why I think that LSTMs, or why I started with LSTMs. The reason is that LSTMs are actually a generalization of any hydrology model that we have. So hydrology models are usually state space models. We have some internal states like soil moisture, snow, whatever, and we update these states as a function of the previous model state, the model inputs, and some model parameters, and the output, which is discharge, is a function of the model states and some more model parameters, right? It's like a general description of the hydrological state model. And the LSTM can actually be described in exactly the same way. The LSTM also has internal states, and the current state is also a function of the previous state, the current model inputs, and some model weights that we learned during training. And the output is also just a function of the current model states and some more model parameters. The difference is that the hydrology model is only able to model any process that we implement into the model and only how we implement it into the model, while the LSTM is able to deduce any process that is important to predict discharge and that can be deduced from the data. So actually in the very, very first LSTM paper that I published in 2018, there's already at the very end, like a sneak peek, which is in the upper right, of what I found in the LSTM cell states back then. I did this like 1 week before submitting the paper, and the paper was already very long, but I was so excited that I wanted to include it. And what I found was that there was one particular cell that every time temperature, which is, right, there's a zoomed in version. So at the top, you see the temperature, the maximum temperature, and in the bottom, you see the cell state value over time. And you can see that as soon as temperature goes below 0, this value is accumulating something. And at the point where the temperature is now like going above 0 again, this value quite quickly declines. So what can this be? I thought it could be a snow cell, right? It looks like snow. It looks like it's accumulating some information during the freezing temperature. And then as soon as the melting season starts, whatever was stored in the cell state value is quite rapidly declined. And I was actually so excited about this that I, for the next half a year, so only made model interpretability stuff. So this was still before the first regional model paper. And at this point, LSTMs did still perform worse than hydrology models. Because my very first paper was training LSTMs on single basins, which I don't recommend anybody to do. So I had another presentation at EGU, and there we looked at different processes that we can extract, like snow water equivalent, snow cover fraction, and evapotranspiration that we took from different sources. And we could actually find individual cells with very high correlation to any of these processes in the model. And again, I had this, because I like to look at the snow cell, it's also one of the easiest cells to find. What you see here at the top is precipitation, at the bottom is temperature, and in the middle is the cell state and snow water equivalent from a different model as a snow proxy for 3 different years. And you can see how well the cell state matches what we with a snow model would model for this catchment. And this model has never seen snow. The only input to this model were temperature, precipitation, and solar radiation and stuff like this. And the output was discharge. But clearly, it has learned snow, right? And not only that, but it learned snow in an individual cell. And again, this is probably no surprise because it's one of the most important processes in any catchment that's dominated by snow. And if the model is able to predict what's happening there, most likely it has learned to accumulate snow information over the winter. So we continued and we wrote a book chapter. Here we went into different directions and we looked in how much history is the model using at any point in time during the year, averaged over many years. And we could see, for example, that, and this is if you only look at the left column now, in the center, you see the median discharge over all years and with the percentiles. At the bottom, you see the median temperature. And at the top, you see for every day of the year, how much history the model is using on average to predict this day. And we can see the same pattern that at day of the year time step 300, which very well accumulates when like temperature in this particular basin usually goes below 0. The model is using more and more history to predict any given day. And this plateaus during the melting season in the summer. And then like after the peak season, it rapidly declines. So the model is really to make any prediction this spring and summer, looking back at the entire history of the winter, because it has to know about how much snow was accumulated to be able to give a good estimate. This was just, again, we want, at this point, I was just interested to see how much does the model understand from the system? And is it giving predictions for like correct reasons? And it's not like, I don't know, taking the precipitation from yesterday and multiplying it with temperature divided by solar radiation or something like this. What we also did was, well, there's a technique that's called integrated gradients that allows you basically to see, given any point in the network, for example, the model output, which inputs at which time step influenced this neuron, for example, the output, in which way. And what we did here was not to look at the output, but we looked at, again, at like one snow cell, and we could see that this snow cell was mainly influenced by precipitation, which is the blue line at the top row. And in a positive way, meaning it is increasing the cell state value. And the negative trend is solar radiation mixed with temperature. And now there's a big but. Everything I said so far was looking at individual cells. And all of it, actually, most of this interpretability stuff that I showed you so far was actually before I joined my PhD supervisor, who is the inventor of the LSTM. And he told me that actually there's no reason why the LSTM is forced to store information about one process, for example, snow, in one individual cell state. For the LSTM, it does matter. It's perfectly possible for the model, if we don't enforce it to do anything special, to store snow as the combination of 3 or 4 different cells, like cell state 1 minus cell state 2 divided by cell state 3 could be the perfect representation of snow. And I so far did not look at this and only looked at like individual correlation of cell states. So I think this was last year, we met Tommy Lees from Oxford, and we did a paper with him. And what we did there was actually, we trained one LSTM on all of CHEMIL's GB, like another CHEMIL's data set, but with data from Great Britain. And this model was trained identically to everything I said so far, like one regional model being trained to predict discharge for all of these almost 700 basins. And after the model was trained, we extracted the time series of cell states. And now we used this vector of cell states. So in this case, I think it was a vector of hidden size 64. And we trained a single linear regression mapping from 64 to 1 for all of the 600 gauges together. So it was a shared linear regression, basically, to predict, for example, soil moisture from era 5, right? The thing is, we need some label to be able to like extract this information from the LSTM. We don't, like the LSTM itself, we don't know where to look for soil moisture or where to look for snow. So we have this one shared linear regression. We mapped it to different levels of soil moisture. We also mapped it to snow and whatever. And we found that we can basically, for all of the basins, recover the upper levels of soil moisture with very high agreement for all of the basins. And you can do this actually with very limited data, because it's a linear regression with, in this case, 64 weights. So you have not a lot of freedom to do anything exotic there. And we had 600 something catchments. So actually, I think we did something using like 1 month of data of all of these 600 catchments was already enough. And I would bet even if you just have like 30 basins and you have high quality soil moisture data in 30 basins, and you just train the linear regression on these 30 basins, you will still get a very good extractor for soil moisture in all of your remaining 600 something gauges. So to conclude this section on model interpretability, what I want you to take home is that it seems like LSTMs are not only good in predicting discharge, it also seems like what they learn internally contains a lot of useful information about hydrological processes that usually are important for academic purposes, but sometimes also for like operational purposes. And you are actually able to get a model that is very good at predicting discharge. And if you do it right, you can also extract information about soil moisture and snow from the same model. But there is still a lot of room for research, because actually, apart from my publication, this one paper from Tommy Lees, nobody did anything in this direction. And there are like hundreds of papers just applying the LSTM. And yeah, I think it would be great if much more people would look also into model interpretability and how we can learn something from the model. Okay, so before I want to give my conclusion for today, I actually would like to take questions now.